this is actually the talk for the seminar series on learning machines. And my pleasure is, my great pleasure is actually to introduce the speaker of this week, and Ruth. Misener is a professor at Imperial College in London. She's a friend, so I will not spend too much time in introducing her, because I know that she will impress you with the talk and not with my presentation. She has been active for a number of years now in giving wonderful contributions on the mathematical and computational and software side of optimization, and starting from the journey from chemical engineering, from which she's still very much attached. And and today she's going to talk about connected things to actually solving hard optimization problems. And indeed, it was a wonderful title about not stopping worrying about parameters. Thank you to be here.
There's 3 reasons I think that you could come to the talk. One is that you might like the optimization. 2 is that you might like the pizza. So please continue going and getting pizza, because let's be honest, why we go to the seminars and it's free food, no matter what level we are. And then the 3rd is that you might like the title. I'm pretty proud. This is like my favorite seminar title.
So you may update your parameters if we go for the pizza.
I might update my parameters if we go for the pizza. Unfortunately, and just warning, I don't do the awesome thing of keeping the analogy going. So if you were hoping for basically just slides of Dr. Strangelove, I am going to disappoint, I'm afraid. Okay. But basically, the techniques I'm going to be talking about today, I'm kind of giving right away the criticism that you might all have, which would be very reasonable, which is to say, good God, Ruth, you use a lot of parameters. And so I've already given you one of the weaknesses of this. And now let's look about whether or not it could maybe ever be useful. So I did this work with a ton of really smart people. A common idea, and I'm interested in solving difficult mixed integer optimization problems, difficult mixed integer nonlinear optimization problems. I'm going to solve these computationally. So when we solve them computationally, I'm going to my backpack. My backpack is not important, and when I'm going to solve them computationally, one thing that I might want to do is I might want to develop good relaxations. So I'm going to be thinking about methods that are related to branch and bound, and sort of how do I sort of computationally expedite branch and bound. One of the common techniques for doing this kind of thing is to use what's called the reformulation linearization technique. And one thing I can do in RLT is I have these equations, say AX is equal to B, and I can sort of multiply these equations by one another. I can say, well, it must be true that AX minus B times AX minus B, well, that's equal to 0, right? Because I'm just multiplying 0 times 0. And I can, this new equation would be redundant in the original problem formulation, but maybe the relaxation of this nonlinear equation would somehow expedite the rest of my line LP, maybe especially if there was already a lot of these bilinear terms, x times x, or something like this. Now, what Shirali and coworkers are known for is that not only do they do this particular new formulation of multiplying 2 things together, sometimes they say, oh, we can multiply 3 things together, we can multiply 4 things together. And of course, what happens is that as you're getting to these higher orders, you don't just have to multiply this equation times this equation. You could, if you had a bunch of equality equations, you can start multiplying them together, and you could just make yourself a ridiculous number of equations that you have multiplied by one another, and just sort of introduce all sorts of silly extra computations that you would have to do. And I say silly because basically once you're getting to these higher orders of the hierarchy, at least for reformulation linearization technique, my computational experience and my understanding of the way also the proofs work is that it starts to be maybe not such a good idea to move just computationally into using these higher orders. Another example that's kind of similar to me, just as someone who wants to do good computations, is the Lasserre hierarchy. Now, I understand there's all sorts of beautiful maths with the Lasserre hierarchy, but I'll just go straight to what me, as somebody who wants to sort of solve optimization problems, looks at, which is that big moment matrix, right? So in one dimension, I might be looking at some sort of Schur complement. In 2 dimensions, I get this like really big moment matrix. The moment matrix gets bigger and bigger. And basically what I need to do at each level of the Lasserre hierarchy is make sure that this big matrix is positive semi-definite. Okay, fine. So what I wish to do sort of over and over again, and sort of the theme of what I'm talking about today, is that maybe I like this strategy for multiplying 2 things together. Maybe this strategy of multiplying 3 things together is too expensive. Or maybe I like this first moment matrix, and I can solve problems with just having saying the first moment has to be positive semi-definite, but maybe I can't handle that second moment or something like that. So what I want to do is I want to develop, that's why I have this between formulations as my title. I want to develop relaxations that are somehow maybe between this level and this level, or between the red and the black. And the sort of admitting right at the beginning where a possible problem is going to be is that the different levels of these hierarchies are often quite beautiful in terms of, well, maybe you can't solve it for higher levels, but you can write it down with very little maths, or you can write it down in some sort of simple sort of way. Whereas a potential problem with what I'm going to do by being between these 2 formulations, I need to pick which bits I'm going to choose from between these 2 formulations. That's where the parameters explode in my face. And that's the comparison to Dr. Strangelove, is that it really is explosive, the number of parameters. Okay, so where I'm going to start my story is in formulating the disjunction. What's happening with this notation is that we have these disjunct indices, and it's an OR operator here that basically either that perhaps, for instance, one of these disjuncts is active or must be true. And then once you have one of the disjuncts is active, then all of these constraints have to be satisfied. I am a chemical engineer and I come from that community. The reason that we like this particular sort of formulation, is that a question? No, okay. The reason that we like this formulation is that you'll have something like a reactor can be on or off, or a reactor can be in this setting or that setting or that setting. And sort of what are the governing rules of the system kind of change between these sorts of settings. Sometimes by already from the beginning formulating something as a mixed integer linear program or something like this, somehow you lose a little bit of information. Maybe it's only for the human, but it's an understanding that in this regime we operate like this, and in this regime we operate like this, and in this regime we operate like this. It's just a different way of understanding things that as engineers we find really useful. So people have studied these problems over and over again. I'm very far from the first person to come up with any kind of sort of big M formulations or convex hull formulations for problems of this nature. But if I had a problem of this nature, then I know sort of 2 major ways of looking at things and 2 major ways of formulating things as a mixed integer problem, maybe mixed integer nonlinear, maybe mixed integer linear. One class would be the big M way of looking at things, where I would add a number of binary variables, just on-offs, perhaps scaling with the number of disjunct indices. I would preserve all the constraint expressions, that's good. There would be a weak continuous relaxation, but simpler subproblems. And then on the other side, basically I could do a different formulation that would still add only the same number of binary variables, possibly add many more continuous variables. Now, if in the nonlinear case, I might introduce the perspective function, which somebody like Andrea doesn't find hard, but I find hard. And then you would have a stronger continuous relaxation and difficult subproblems. So basically, what the sort of heuristic result that you see commonly in the literature that people will say is that they'll say, well, this is a stronger continuous relaxation, but this one is the one that people will more often use just because you can solve every subproblem much more fast. And I assume you all know all the work that Andrea's done, but one of my very favorite papers from the last 10 years, I make everybody read it. It's basically he is going from big M, and then he's reducing these parameters that make the big M so terrible over time. So hopefully, actually, our approach would still kind of work with that kind of idea. What we're going to do is that today we're going to be talking about somehow being in the middle of big M to convex hull. And the way that we're going to do it is that we're now going to develop intermediates between those two extremes, sort of trying to find some sort of Goldilocks strategy between the two, where now the number of new continuous variables is going to scale with my magic number n. So now I've got this magic number n, number of new continuous variables that are going to complicate the problem. The problem class that we are looking at is that we are looking at these functions g being convex and additively separable. So I can rewrite my g as a sum of the h's. When we look at this sort of more broadly, I basically haven't figured out how to relax the convexity assumption. So it isn't such a great approach for nonlinear non-convex, but the additively separable can be relaxed a bit to the partially separable. The functions are going to be bounded. The far fewer constraints, the number of variables. This is an engineering choice that's just based on our observations. And then the far fewer disjuncts, the number of variables. That's because now my number of continuous variables is going to scale with my number of disjuncts squared rather than my number of disjuncts. So basically, you'd better hope that that n is much smaller than that d. Okay, so it's a funny setup, but I argue that there are a lot of optimization problems that follow this particular setup and are somehow important there. The one that I've gotten the most traction from in the engineering community is that you can, if you want to formulate value neural networks as a constraint, where it's a constraint in your optimization problem, then you follow this one, which is nice. Okay. And here's basically what we do. So those G's were additively separable. Now they are my H's. And basically what I have is here is my disjunction. The first thing that we're going to do is we're going to lift to a higher dimensional space. And for each one of the disjunctions, we're going to introduce as many new variables as my new magic number n. And basically what's going to happen is that we're going to divide up these the sums of the h's so that each one of the sums of the h's is less than or equal to one of these alphas. And then we put the alphas, we sum the alphas to be now less than or equal to this constraint. So what you can see is that if this capital N is equal to 1, all this is basically having all the same sums of the h's less than or equal to one new variable, and then that one new variable being less than or equal to b. So all I've done is introduce some new variables at this point. Whether or not that's a good idea, well, I don't know, but it's a higher dimensional space, right? I haven't changed anything yet. Now what we're going to do is we're going to now relax these constraints that we had split up. So basically these h's had been split up just for one disjunct indices. The h's would have been split up into as many bins as n. Now what we're going to do is we're going to relax all of those h's to global constraints. So what happened here is almost like a linearization, right? Because what we had was we had all of these constraints that were inside of the disjunct, and now we are replacing basically the sums of the h's with an alpha. That alpha is staying inside of the individual disjuncts, and then the sums of the h's less than or equal to the alphas is now relaxed to a splitted constraint. This is not, if you, at any of the points that are integer feasible, this is not a relaxation, but at points that are not integer feasible, this is. Okay, so what I did, which was nasty, that many of you have already probably figured out, is, okay, let's say I had as many etas as, say, 36 or something like this. Well, then each one of my alphas and each one of my disjuncts is going to have all 36 elements inside, okay? And then what's going to end up happening is that, let's say now I've decided to do this, n is equal to 2, and so I'm going to split in each one of these disjuncts, there's going to be an alpha 1 and an alpha 2. Well, then I could have divided up all of the indices with, half and half, or I could have done half and half in a different way or something like this. So basically, a possibly problematic aspect of what I'm doing then is that basically my computations are going to be based on whether or not I split things correctly into these bins, which is going to be something I'm going to have to think about. Okay, so once we have lifted to a higher dimensional space and then relaxed the constraints that were inside this disjunction to be global constraints, now we are going to just use the Polish extended formulation to now get the convex hull, not of our original disjunction, but of that new formulation for the disjunction that is right here. One of the things that did, because I effectively linearized this disjunction, is that we're avoiding the perspective function, which can be annoying at some point. We are now doing some sort of, we are getting the convex hull with respect to something that is lower dimensional.
Just a clarification for this HIL functions. What are assumptions on this HIL?
The HILs, they need to be in the proofs, they need to be additively separable. So basically, something like a x1 plus x2 separable, and then they need to be convex. The convexity is not straightforward to relax. The additively separable is more straightforward to relax.
So here you kind of lift it to a higher dimensional space, but gain you're kind of linearizing this HIL by replacing the plate.
Exactly.
And take this convexity outside of the disjunction.
Exactly. Okay. So what happened from the feasible X space stays the same from the original disjunction. The 1 split is equivalent to big M, so that would be putting everything into 1 bin. If H is affine, an eta split, which would be basically every single one of the variables, would be equivalent to the convex hull. And as Omar just said, that's exactly, because I did that linearization, that's why an eta split is not going to be the convex hull if I have something that's not linear. And then also, if H is affine, we can think of this kind of as a hierarchy where I had 1 bin and I split it into 2. I'm going to get something that is as least as tight. Okay. So one of the applications, I'm going to give in a set of applications that's easier to say, but not the applications that I tend to use when working with applications people. But just as an example of where this kind of stuff can come up, optimization over trained neural networks. So I'm given a neural network as a found object. It's my neural network, and I'm given an image. Here it's a 9. I'm given a label. It's a 9, and I want an adversary, which would be a 4. An example of an optimization problem that I could solve over a neural network would be what is the smallest distance that I can move, say, using the L1 norm, from this image to a different image, where now instead of saying, oh, it's a 9, my neural network is going to say, oh, it's a 4. So my example is pretty weak, just because I want to get through an example quickly. But I hear plenty of people interested in performance of neural networks and stuff. So what I might want to ask, for instance, is what is the smallest distance from this image to an image that predicts that adversary 4, and then I could use different metrics. So maybe I use the L1 norm, maybe I use the L infinity norm, et cetera, et cetera. There's a large number of optimization problems that I could solve with basically a neural network being a constraint in my optimization problem. I work a lot, of course, with engineers because I am a chemical engineer, and the applications that we are often interested in is that you'll have one constraint that was learned from data. You have some sort of reactor or something like this that you don't have all the equations for, and instead you say, okay, it's about following this behavior, and then you have a bunch of other equations you can write, like flow in this equal. Okay. People who are good at what they do have thought about big M formulations of, for instance, a ReLU neural network. What's fairly easy to do, well, easy after Matteo did it and then sort of shows us the rest of us how to do it, is basically you can just think of these neural networks as being nodes that are repeated over and over again. And if you just mind your inputs and your outputs, you can have just a formulation for a node and then connect all the nodes together. We're going to be doing ReLU, so a max function, either 0 or something that is affine. But there's, of course, plenty of variants that we can look at. The things that were variables in the training procedure are now parameters. So my weights and my biases are now parameters. My x's and my y's, the inputs and the outputs to the node, are my new variables. And basically, I can think about, for instance, a big M formulation that's going to decide whether or not y is equal to 0 or y is equal to this affine function. And then you either use Andreas' clever strategy of getting these things to these LBs and UBs to shrink over time in the course of a branch and bound tree, or you kind of hope that you did a good enough job estimating them in a good sort of way at the beginning. Then what I would like to do is I would like to improve big M, because Garobi and Cplex and all these guys are so good that a lot of people in these communities who are doing AI verifications are really just implementing big M, and then they're using Garobi because Garobi's better at the SAT problems than SAT solvers, which is crazy.
Sorry, just might jump to questions because as I said in my comment.
Yeah.
So if you introduce these two approaches, like the big M and the convex fold.
Yeah.
So at the end, what would be how would you judge the quality of the solutions? You're just looking to the running time of.
It's only running time. It's very experimental, right?
So it's going to be the running time. Are you saying so? And then basically your method is kind of bridging the gap between.
It's wanting to. Yes.
The two. So is there basically an optimal number n of splits that would basically get you something?
Yeah. Let's skip right there.
Better than both approaches?
Exactly. So what it is it's one of these things where if you just told me to pull out of my hat, prove to you what is the best value of n, I would have to say, no, I'm sorry, I can't do that, right? So it's going to be heuristic, and then somehow I'm going to hope that some problems are similar enough to one another that I make good judgments. So this is for one neural network that we trained, and then we are just experimentally only varying this value of n. N is equal to 1 is just big M. And then basically what we are seeing for this particular type of problem is that the number solved for n is equal to 1 looks good. Then I can get a larger number solved for this problem with a higher value of n. And then what is happening is, what is the value of n I should choose? Well, it looks like n is equal to 10 is awfully heavy and not doing such a great job. It looks like for problems that are going to be easy anyway, n is equal to 2 is going to be good, but then it's maybe not going to be as good later. But this is also something, this is so experimental, right? And so what I'm going to do is I'm going to hope that I do a good job of, for a particular problem class, of doing good choices.
Yeah. A quick question was just this. So for n is equal to 1, you are recovering exactly the big M.
Yes.
Constraint. So as you move from n is equal to 1 and you're increasing, can we, find a case where like you're gonna do worse than both, than big M and convex?
Oh, sure.
So you can
exactly. Yeah.
So you could just so you could start from n, and at least you say with n is equal to 1, I'm recovering already big M, and then I probably return the best out of.
So basically, actually, the way I should answer that more in a better way is, there are definitely places you're going to be worse than big M. It's very hard to be worse than convex hull if that was your whole formulation, just because convex hull is too heavy for this kind of problem. The way that people integrate the convex hull when they integrate it is that they do it as cutting planes. So what is happening is that the new constraints that we are introducing into the problem, basically these splitted type things, they end up being a subset of the cuts that you would take if you were just looking at the convex hull. So it's a subset, but so there is nice work that thinks about convex hull and adding those as cutting planes. But then I am sort of picking winners at the very beginning. And so there are trade-offs there, right? And yeah. Okay. Good. The other thing that I'm going to have to do is, I could show you how the mathematics works for the moving to the partition with the ReLU neural networks, but Omar asked questions past it already, and it's basically the exact same as the initial slides that I showed you. The other choice, in addition to this parameter n that I have to choose, and maybe I do a good job and maybe I don't, is I also have to decide how to do the binning. Let's decide I've chosen n is equal to 2, and now I have to decide who lands in each one of these bins. And what it is it's basically, let's say I have 4 inputs to my node in my neural network, which I realize is much more sparse than neural networks really are, but let's just say 4 inputs to my neural network, and they have weights 1, 100, 100, and no bias term, for instance. And then I'm just in this hypercube between 0 and 1. Okay, well, I could put x1 into one of the bins and x2, x3, x4 into the other one of the bins. This right here would be a really great approximation of x1, right? Because this would do a great job of sort of adding the bits of the convex hull that were somehow related to x1. But somehow there would be a really bad approximation here of x2, because basically, if x2 is towards 1 versus if x2 is towards 0, it's kind of going to get lost next to those 100s. Another way that I could do it is I could say, well, I'm going to put weights that are very different from one another in the same bin. So I could put the one with the 100 and the one with the 100. This way, I think, or my impression is, this would be a nice approximation of x3 and x4, but maybe it would not be such a good approximation of x1 and x2. Or I could put equal weights with one another. Okay, the way that I propose that we do the partitioning is that a couple ways. Is one, that we look at equal sizes of the binnings and then have the weights in each one of the binnings be as similar as possible. Another way that I suggest that we do it is to look at equal range. So don't worry if the sizes of the bins are similar to one another. Just have the W's be as similar to one another as I can make them. And the way I will try to show that we have something that is somewhat reasonable is that I will compare this to random partitions, where I'm just sort of assigning indices at random, and to uneven magnitudes, which would basically be putting the 1 and the 100 together, if possible. There's more details on the computations in the paper itself, because of course a lot of this kind of work depends on my ability to do computations that are reproducible. So on the left-hand side, I want to be up because that would be a higher number solved. So if I want to solve more problems, first, all this graph says is that optimality-based bounds tightening, which I know and love from mixed integer nonlinear programming, and also is known to work for this class of problems, works, which is something that should happen. So basically, the dotted lines are optimality-based bounds tightening, and the solid lines are just interval arithmetic. And then what happens is that the blue formulations are trying to keep the weights similar to one another, and the red formulations are either weights being purposely dissimilar or weights being just assigned at random. And so either with optimality-based bounds tightening or with no optimality-based bounds tightening, we are solving more problems if only we do the binning in our proposed strategy. So this is the kind of thing that gives me some amount of hope for that ridiculous number of parameters, is that at least I have a kind of reasonable way of assigning inputs into bins, whether it's the reasonable way, I'm sure there's something better, but we have something. Then, so I want to be up on that graph. On this graph, I want to be down, so average time solved. Basically, what's going on here is that I want to be down, and so optimality-based bounds tightening is again doing better. So basically, you're going to solve problems faster if you use optimality-based bounds tightening, because I am not in this particular example incorporating the time that it took me to do the optimality-based bounds tightening. So I've done optimality-based bounds tightening on all of these problems, and then I solve them. So of course, the ones that have had it done are going faster. And then again, the blue versus the red is doing better, whether or not you used optimality-based bounds, which is nice. Okay. So basically, what I would like to do in an area like this is I would like to be able to solve problems that people couldn't solve before. If I'm just going to speed up a solver by 10%, well, Tobias Achterberg's going to do that next week anyway, so why bother? So I want to be able to solve problems that other places can't solve. So we claim that there are problems where that you couldn't solve that now you can solve, which is nice for a variety of different examples. You can find some where we're doing better, some where you're doing worse. I have it from Pierre Bonamy, who has implemented this, that sometimes this is better. So that if Pierre agrees with me, then I think I'm doing something right. This idea can also work with the cutting plane idea. So basically, the things that we're adding as constraints at the beginning, rather than adding them as cuts in the middle, we could alternatively think about sort of adding some of the constraints at the beginning and then adding some of the things as cuts later. So that kind of works, but not really. So let's see. And then this end split idea, I was presenting it with respect to neural networks, but of course all of the proofs worked for functions that were non-linear. So what's going to happen now is that I'd like to look at this constraint that is right here. It's in 4 dimensions. So when I project onto x1, x2, it looks like the 2 black circles. So basically, the feasible set is the 2 black circles. One split is the exact same as big M, and it's going to give a feasible region that is the gray. So that's familiar, big M not doing very well. I can also do a 2-split formulation, so I follow exactly what we recommend. The gray region gets smaller, which is what I like to see. Then the gray region is going to get smaller again if I move to a 4-split formulation. Now, this is where I can start talking a bit. I mentioned that in the linear case, we did have a hierarchy, and we are going to the convex hull. Here with a 4-split, we have divided everything into the number of variables. But first off, you can see that this isn't the convex hull because there's all this extra bit on either side. So that's one thing. So basically, one of the things that happens with some of this partitioning idea that we have is it's a really stupid formulation if you could solve with the convex hull. So basically, with the neural network idea, at least what was happening there is, well, I can't even sort of, I can use those cuts. I can use the cuts from the convex hull as cuts, but I can't really put them all in as constraints from the very beginning. But if I only was in 4 variables and I was able to do the convex hull formulation, well, this is a terrible approximation. And basically what's happening is that it's the linearization step that's killing me here, is that if you had properly used the perspective function, then you would have gotten the little bits on either side cut off. Another thing that's happening here is that I only claimed I had a hierarchy when I was in the linear case. And one thing that you'll notice is that you have this nice kind of rounded edge where the light gray is touching the dark gray right here and right here. But then you'll notice that for the force split, you don't actually have a proper subset of that 2 split. So there's this nasty little triangle that's coming out here and this nasty little triangle that's coming out here. Where that is coming from is basically from the big M parameters that you're using, is that sometimes those big M parameters from those intermediate ones can be useful somehow. And so the things that I lose with respect to the either big M or convex hull idea, and the reason that it's not a hierarchy to a convex hull is one, the linearization. Actually, it's just the linearization. It's the linearization. Then there is that big M parameter that you're fixing, and that's causing those interrelated problems. This is also related to our sort of standard thing that we find in MINLP, where in MINLP we're forever sort of taking things that are complicated and saying, well, that's too complicated for me, I make a new auxiliary variable. But then sometimes those auxiliary variables aren't quite related to one another in the way that they were originally. That creates a problem. That's exactly the problem that we have here as well. Okay. And this is saying it a bit more clearly, is that the 4 split is not dominating the 2 split because of basically the big M parameters and also the linearization issue. Now, I still, even though I think that it's, it's no silver bullet, and in fact, it gives maybe a little bit too many possibilities intermediate to big M to convex hull. We still do find that for these nonlinear problems, we can be beating big M. And so basically, what's happening here is that we are looking at sort of time to solve and number of nodes explored in big M versus these splitted formulations. And as expected, what I'm going to find is that consistently across the board, you're going to take, on average, experimentally, right? I can only say it experimentally, fewer nodes in the branch and bound tree to be able to handle those splitted formulations. And then oftentimes I'm going to get something where the time is also much better. And in particular, I'm able to solve problems that I couldn't before. So you, of course, have the problem with, your Goldilocks strategy requires you to sort of figure out what the parameters ought to be, but it is useful to have. The other thing that I like about stuff like this is when you start thinking about sort of splitting the constraints. I mentioned that you end up with this same issue where an x1 in one part of the problem doesn't know it's related to an x1 in another part of the problem, which is exactly the issue that we get with MINLP. And one of the things that I like about this is that I can use exactly a solution from MINLP for this. And so Pietro has this nice paper on feasibility-based bounds tightening based on pairs of constraints. It's the exact same thing as what he has in that paper. It's basically just introducing these constraints, maybe a posteriori. An issue with this particular, so what happens here is the one split is atrocious. You know, you have your two feasible regions. Your one split is just sort of the whole thing. A two split is going to reduce part of the feasible set. And then the two split plus these linking constraints, it's not going to be the convex hull because there's all this extra bit right here. But at least you're reducing things further. A downside of this, and why I think this work is not implemented in the solvers, if I know correctly, or not on by default, is that there's an awful lot of these constraints that you could possibly put together, and sort of picking which ones to use doesn't always seem to be easy to do. Okay. So I like this idea when, for a particular problem class, a good set of parameters consistently stays good. I understand that's an experimental result, but if a problem class is important enough to me, I might be willing to do that kind of thing. There's a whole bunch of implementations of this at this point. So the Paolo team implemented it in their GDP plugin. The nice things that I like is that we avoid the perspective function, which I appreciate. Tighter than big M, sometimes easier subproblem, or easier, definitely easier subproblems than convex hull, and sometimes a hierarchy. And then we can use these well-known MINLP strategies. There are an awful lot of parameters. The linearization is going to loosen the relaxation, and we have this function interdependency that is lost. And we also have this code omelet that's basically our way of sort of translation into real world type things, where we are going straight from an onyx neural net into something like the other story. I have another story, but I always end up talking so much about one story that it's difficult to talk about another. I'll take questions now, and then can show briefly this other one if there are questions. Yeah, please.
No. So the first question is, I remember you said the big M can compress a neural network, but it seems it increase the number of the parameters. You have add a binary variable to reformulate the value.
Oh, if I said compress, that would have been a bad word. So to formulate a ReLU neural network using a big M formulation, I have to introduce as many new binary variables as there are a number of nodes in my network.
So you represent the binary variable as a node.
I represent the binary variable. Well, okay, there's a simplifying assumption that I'm saying there, which is it's a good thing to call me on it. So in that statement that I gave to you, I was assuming that we are a fully dense feed-forward ReLU neural network, and at every node there is only a ReLU function. So basically, if I was to do so in our omelet code, we also do convolutional neural networks, for instance, and all we do is sort of reformulate the convolutional by sort of changing matrices around. We sort of reformulate the convolutional neural network to just a feed-forward neural network. And then if I was to have something like a recurrent neural network, I would have to repeat the binary variable every time I went through the ReLU function. If I had something like a graph neural network that had edge features, I would have to, as many ReLUs as I had, I would have to have that number of binary variables. If I had something like a max pooling layer or something like that, I would have to have a new binary variable for max pooling. Now, all of this is clearly introducing huge numbers of binary variables, right? Yeah. Which is sometimes going to be okay, and sometimes it's going to be a stupid idea, right? And so another way, if you know Sven Lasserre, what Sven Lasserre says to do is to instead of introducing a binary variable, he's going to introduce a complementarity constraint. That's basically the complementarity constraint is you're either on the slanty bit or you're on the flat bit. So then you could solve it perhaps using a nonlinear optimization solver, or you could have a different a different activation function, and so like a sigmoid or something like that. So our omelet code, for instance, we worked with Carl Laird, who's a big nonlinear optimization guy, and so we do both ReLU. And so it's one way of formulating a feed-forward ReLU neural network that only has ReLU activation functions and nothing else.
Okay.
Would be one binary variable per ReLU activation. Yeah, you're right that I need to clarify that kind of stuff. Yes.
Would it be possible to use different split sizes in different subtrees of the branch bound tree?
That's a really, really good question. So in fact, that's exactly what we do for a bunch of practical problems. Because what happens is, I don't know if you've ever seen like global dynamic optimization, but what happens in something like global dynamic optimization is you have your bounds, and then in the next time step, the bounds get worse. And then in the next time step, the bounds get worse, right? And we have the exact same problem, because if we have something that's a feed-forward neural network, your big M parameters start bad and they get worse, right? And so what we do and what works computationally quite well in our experiments is that basically we will do a higher number of partitions on that first layer of the ReLU neural network, where you can actually hope that some amount of information from the bounds on the original input variables can help you. And then after that, we might just use a big M formulation or something like this, because a bad approximation is a bad approximation. And as long as I have a bad approximation, why would I introduce more continuous variables to represent my bad approximation?
If I recall correctly, in the original paper by Fischetti, they also try to tune these bounds, right, with maximizing inputs beforehand.
In
the benchmark, or?
We are specifically using the big M formulation that comes from that Anderson et al. Paper that has from Pablo Diama and other friends. What happens in that paper is that they get what they are saying, or what they prove is the tightest big M that they get, and so we. I do semi-definite programming at a rush, or should we do? What should we do? Everybody gets 10 minutes of free time.
I don't know. I mean, it's up to you. If you want it, I mean, definitely, if you have a punchline for the semi-definite.
I have a punchline. It's the exact same punchline. That's the thing. It's the same story twice, right? Which is why I'm never, so absolutely it must go to another. Basically, we all know max cut, and we all know and love max cut. We've got these. I've got a smaller moment matrix, a bigger moment matrix. What I could decide to do is either I could sometimes include the second moment matrix for some, those of the subclete. Basically, we're using the sparse SDP way of thinking about things from Wacky et al. And then basically you end up with a bunch of these smaller semi-definite constraints. And so basically we can either go up to the second moment matrix in Lasserre hierarchy sometimes and not others, depending on what we might like to do computationally. Or what we can do is that we can include some augmentation. So basically we could say, well, I will say that, I take a subset of the rows and the columns, and that subset is going to be positive semi-definite as well. I can include that as a constraint. So basically, the only thing that we really have to guide us is how big we're happy for our moment matrices to get, and how big our clique sizes are, and then it's a bunch of computation to basically decide what to do in a nice kind of way. But it's the exact same story where you hope it works sometimes, and you basically have things blowing up in your face.
One question that comes over this is, which is quite obvious, is there space for learning this for specific classes of programs?
Wouldn't that be cool? Yeah. I would like to think that there would be some opportunity.
I mean, really learning what is the right. I mean, you can change the size during the entire branch and bound, but so at the moment you just have some heuristics that are telling you what to do. I mean, some indicators that are
exactly. We only have heuristics, and a downside of this. You know, I was getting to talk to Ruth about re-optimization, right? But a difficulty of these kind of strategies is I'm going to sort of pick once. And so maybe in a re-optimization strategy similar to what you were talking about, that would be the only kind of thing where if I've had similar enough problems that something would work.
Other questions?
I think maybe the random neural network, if you reformulate the combinatorial optimizations,
yes.
So you can solve it by obtaining a global optimal.
Yes.
So neural net typically find the local optimal.
Keep in mind when I say remember that the optimization problem that is solved over neural networks is typically training, and that's where people typically talk about local optimization. What I have is we already have the neural network. I act like it's a found object. It's never going to change. And then what happens is I wish to optimize over it, right? So where I might end up with this kind of application, I gave the one application that was the figuring out if my neural network was doing a good job of predicting images. But then in my engineering land, what ends up happening is that these already trained neural networks, I want to use them as part of a larger optimization problem. But there's no training involved. So I assume somebody did the training and they're happy with the training.
So no training, just solve the optimization. At least it's much faster. You don't need to take a stochastic gradient, take a long time for training and testing. Your methods directly can solve the optimal solution. And then
it's just a different problem. It's not that if I would not be faster than I recommend to still use stochastic gradient descent to train neural networks.
So the difference on here is that when it's really trained, what is the variable of the problem is the input. The input is variable, right? I mean, she said it. So you're looking at the X now. They are not fixed. It's not a fixed data set, but it's something that you are trying to synthesize an input that is bad for your neural network.
Okay.
So X, which is generally a parameter for fixed for the training neural network, now is a variable. So it's a parameter in machine learning wording.
It's basically maybe a simpler way of saying it than I was saying it earlier, because Andrea's explanation is great. You're just solving the inverse problem, right? Is that instead of solving the forward pass problem, I want to solve the inverse problem of what should the inputs be to get that desired outputs.
You see some feedback loops, right, to make your network more robust. That's what people also.
Yeah, so that would be one possible way that we have some users who are using it that way, is that they'll integrate these neural networks into larger optimization problems, and then of course the neural network just finds the place that the neural network is the most inaccurate, and then you can get some of it.
So thanks.